education. I see you have the textbook there. In my rush to get here to class, forgot to bring mine, but that's okay. I can survive. I will be using Moodle and OneNote heavily. Moodle is where you'll turn in assignments and things like that, at least for now, unless I get, I forgot what it was. Blake showed me a better homework site, but yeah, for now it'll be Moodle. And the OneNote, you can look at the lectures and follow along there or go back and review them. Or of course, like I said, you'll be able to go to YouTube and watch the lecture if that excites you, which it generally doesn't. So today, just our policies. The policies are pretty simple. We will have periodic quizzes. Actually, I didn't think about the logistics of that. You take a quiz. I guess I could just have you guys grade your own or something because, you know, take a picture and send it to me. Yeah, I'll probably just do that. I can trust you guys, right? I don't know. Okay. I expected a little more. Yeah, I'm trustworthy. Well, the big problem is with only 2 students, if one of you is absent, that's like a problem because you want the class to be keeping up. And if one person's not there, that person falls behind. And so to try to encourage that, I always do. If one person is not here at the start of class, I just do a quiz that harms the other one because the whole class is going to be harmed by them not being there. That's my theory anyway. The idea is to make sure you're there. But we'll have periodic quizzes just to make sure we're keeping up, that you're not like, wow, we haven't had a test in 3 weeks, and I don't know if I understand anything we've talked about since then. Daily homework, let's make that weekly. The homework, there's a homework due on Wednesday, and it's a homework problem that I expect you can't solve, but that's okay because I also gave you the solution. I gave you the problem so you can see how I want you to show your solution. I don't want to just see math and an answer with a box around it. I want to see words describing what you're doing and showing that you understand how the pieces fit together and weren't just able to crash some equations together. So, you know, for this first homework, if you look on Moodle, actually on Moodle, it just has the questions. If you look on OneNote here, I assume you guys are all hip to OneNote, right? Since I'm doing it because Blake turned me to doing it. You have here is the homework problem, and here's the homework solution, right? So you can see how I expect the homework to be done. That's the goal here. So hopefully y'all get 100% because all you have to do is write in your own words and show that you actually understand what you're doing. But I don't want there to be any confusion about what is he expecting on the homework. Similarly, I want the same kind of solutions on exams. I want to see the process, the thoughts, not just math. When I was an undergraduate, nobody drilled that into me. I got to graduate school and my teachers were like, what the heck have you been doing? So I aim for my students to not have that discomfort. So midterm exams, there are 3 midterm exams, 1 final exam, see how they break down. Nothing really special there. Note that the final exam is comprehensive. It's kind of hard to not be comprehensive because we're just building up and building up. Already talked about the attendance policy. I mean, you must attend. If you're not able to make it, you know, like say you're sick, let me know beforehand. Give me a call. I'm not sure if I put my phone number here. Let's figure this out. I have a Google Voice number that I use. And of course, I don't know my Google Voice number personally. It is 626-872-4337. Or for the astute, that's 626-8RAID. Yeah. Because I'm a Raider fan. With Google Voice, you know, you get to choose, and I did. So, you know, you can call me, let me know what's going on. I do warn you that I actually always have the ringer off. I hate phones, basically. So you probably will have to leave a message still when you call my number. But then I'll get a text message when you leave a message, so then I'll know. Any questions before we actually start talking about quantum physics? No? All right. So quantum physics, as I understand it, it starts earlier than we usually think. You know, you go back to Gustav Kirchhoff, who discovered that, you know, you have black body radiation. That is, if something is hot, it gives off radiation. You probably studied that like in general physics, college physics. What do you guys call your physics class? The first one you took?
University physics.
Okay, university physics. I would do well to change the names of our classes, because the textbook I use for college physics is named university physics. And the textbook I use for general physics is named college physics. So the students in college physics have, yeah, you can see the confusion. So I'm sure you've learned about black body radiation. You may not have seen 1859 and Gustav Kirchhoff with it, but you know that things give off radiation. That is, they give off electromagnetic waves because of having a temperature. When it was discovered, they didn't know it was electromagnetic waves, but if it's hot enough, they knew that it gave off light. So an incandescent light bulb is giving off light because it's hot. And so Gustav Kirchhoff did some of the original work there, showing W here is the energy density. And depending on where you look, you'll see a W or a lowercase u for the energy density. It's the energy per unit volume that you have. And the energy density here is 4 times the intensity over the speed of light. That was something that Gustav Kirchhoff figured out a long time ago. Jump forward to 1894 when, I think his name's probably pronounced Wilhelm Wien, but we always say Wien because, you know, we're Americans and we pronounce things whatever way we want. He determined that the energy density for a black body was proportional to some function of wavelength multiplied by temperature divided by wavelength to the 5th power. And he further divined this relationship that I'm sure you've learned, Wien's law, that says that the peak wavelength is equal to just a constant number divided by the temperature in kelvins. You guys know that, right? Now, here's something that nobody taught me when I was an undergraduate. If the peak wavelength is at 500 nanometers, how do I find the peak frequency?
The speed of light equation.
That's what I would have thought too, right? Because you know that the frequency, which we will use the Greek nu for frequency, multiplied by the wavelength is equal to the speed of light. And so you would tend to think, okay, so I just put speed of light divided by the wavelength, that should be the peak frequency. It's not.
That's the minimum frequency, right?
Well, it would be, because we're talking about the peak in the energy, you would have thought it would be the peak again. But it's not, because when you talk about the peak frequency, you have a continuous distribution. It's kind of like if you think about, you have a computer guessing a random number. And if you have it guess integers between 0 and 5, the chances of it getting pi rounded to 1 decimal place, that's 3, is pretty good, right? 0 to 5, technically, that's 6 values. So it'd be 1 in 6. And if you say, well, let's add 1 digit, 3.1, well, then it's a much lower probability, because you now have, what, 60 different values? And if you keep adding digits, the probability gets smaller and smaller. And so if you get out to pi as a number with infinite digits, what are the odds of the computer randomly picking all of those infinite digits? 0. And so that's the same thing we would have here. If we look at the energy density at a specific frequency or a specific wavelength, we're going to get 0, because it's continuous distribution. So we have to have some width to that. So we talk about the energy in some width, d lambda, or the energy in some width, d frequency. But we always use linear things. So d frequency and d lambda don't have the same width as you go from one side of the spectrum to the other. And so that's why the wavelength with peak wavelength is not going to match the frequency with peak frequency through this equation. And that's actually what is being shown by that conversion. shifting from the energy density as a function of frequency and temperature to energy density as a function of wavelength and temperature. So you would take, if it's the one that's the density in terms of frequency and temperature, take the derivative with respect to frequency, set the derivative equal to 0, and solve for the frequency that's peak, or likewise for the wavelength. Okay, so that's just something that was a curiosity that I had never realized actually until I became a teacher. So Wien's law is illustrated in this picture showing how the peak wavelength adjusts with temperature. You've learned that, you probably used it. You know, the peak radiation from the sun comes out to be somewhere around, what is it? I think it's 500 nanometers, something like that. Easy to calculate. Now, trying to calculate what shape we have for this curve. So this curve here, this is the shape of the black body curve, very poorly drawn, in my case. To try to find that, Rayleigh and Jones, I think independently, or I don't remember if they worked together or not, but they came up with a solution that came from using standard physics techniques. You probably have heard of the equipartition theorem, which says that if you have different modes that energy can be held in an object, that it should just have the same amount of energy in each one. So that's why, for instance, for an ideal gas, of a monatomic ideal gas, it has just 3 degrees of freedom. And for thermodynamics, instead of kT, it's 1/2 kT. So you have 3/2 nkt is the total internal energy for monatomic ideal gas. If it's diatomic and it's really cold, it's still 3/2 because you don't have enough energy to get rotations to occur. So a really cold monatomic or diatomic ideal gas doesn't rotate, which seems really anti-intuitive. That is a quantum physics result. If you warm it up to room temperature, you have 2 degrees of freedom for rotation. If you have diatomic, it can rotate like this and have energy. It can rotate like this and have energy. But rotating like this will have no energy because all the mass is on the axis. And so that it goes from 3/2 to 5/2. And then if you warm it up really hot, then it has enough energy that it can have vibrational modes. It adds 2 more vibrational modes, and it's 7/2. So basically using that same idea, except for it's kT instead of 1/2 kT per degree of freedom. And the number of degrees of freedom for a standing wave in a cavity, in a resonating cavity, is determined, and we're not doing any derivation of this, to be 8 pi frequency squared d frequency over speed of light cubed. So putting those together, you get the energy density in some width d frequency, remember nu is frequency, is the number of degrees of freedom multiplied by the energy per degree of freedom. And then we see this word catastrophe. Who can point, you may or may not have heard the term ultraviolet catastrophe, but can you point out what is catastrophic failure in that equation? No? I saw Chris trying to mouth something, but I heard nothing. Well, here's something. Go ahead.
Well, I want to say it's when it's equal to 0, but I'm not sure. I guess I'm still. What is P again?
Nu.
Yeah. Okay.
It looks like a V. I know.
Yeah.
So, well, here's the thing that's catastrophic. We know that we can't create or destroy energy, and energy is finite. But according to this equation, at any temperature, doesn't matter what temperature you have, you could be at just a shade over absolute 0. You could be in the microkelvins. As your frequency gets very large, that is ultraviolet, high frequency, then you have that high frequency squared. You're approaching an infinite amount of energy in this small piece d nu of frequency. And so that says that no matter what the temperature is, microkelvins, it's giving off an infinite amount of radiation. That is catastrophic failure. We know it can't be true. And so this work, the research that, well, not research, the calculations that were done by Rayleigh and Jones, Jeans, I'm pretty sure it's pronounced pretty close to Jones. I don't speak French, by the way, so I'm just guessing. It was perfect as far as the physics they understood, and it gave them the wrong outcome. And so we have this ultraviolet catastrophe. Here's a graph showing what the two curves look like. This is the actual curve. And yes, this graph that I took from hyperphysics calls it the quantum curve because it is fit by Planck's solution versus the Rayleigh-Jeans classical one, perfectly done, clearly incorrect. And so that threw the world of physics really into a spiral. What's going on? We don't know. And so we enter Max Planck. And yes, I'm pretty sure his name is pronounced Planck. Everybody says Planck, you know, like you walk the plank. So he received a telegram one night that told him that at low temperature, the behavior of the radiation, and, you know, just described how the curve was. And he had a dinner guest that night, talked things through with the dinner guest, sat down and sent back a postcard saying, well, in that case, this equation should fit the curve. And in fact, that is what's plotted in this. It is the perfect fit. So Planck had a solution, that is, he had a fit to the black body curve. What he did not have was a reason for that to be true. And you guys have studied physics enough to know that if you work a problem and you get the wrong answer, you're frustrated. If you get the right answer and you don't know why you have it, you're probably even more frustrated because you're like, okay, so magic, is that what the key is? Magic? And so Planck has a curve that fits just based on his understanding of curves, but no reason for it. And so then he sits down and just works his tail off trying to find, how could this be true? And I see that I forgot to change the font there. New, of course, looks like an N in some fonts. And he said that if the energy comes in quantized packets at a given frequency nu, the energy can be 1 times a constant times the frequency, or 2 times that same constant times frequency. You know, so it can have 1 packet, 2 packets, 3 packets, 4 packets, but it can only have discrete amounts of energy. Then the statistical calculation for discrete amounts is a different result than the statistical calculation for a continuous amount. And if he had a discrete amount of energy that came in packets of this energy, so the energy of a packet is equal to some n, where n is just a counting number, times this energy h nu, where h is the self-named Planck's constant and nu is the frequency, then he could give a theoretical explanation. So Planck came up with a quantum theory. Quantum mean you have quantized units, specific units instead of continuous, that would explain why black body radiation occurs. So this is, to be silly, a quantum step forward in our understanding of black body radiation. Let me see what I did there right. I cracked myself up. At least one of us is laughing. So that's a huge step forward. Now, funny, at least as I understand it, Planck started this idea, and he proposed that that was what was occurring, but he didn't really believe it as far as, I have no reason for this. It's just, if it's true, then it works. Well, then you enter Einstein. Einstein, at this point, he was working at the patent office, as I understand. He liked to get together with his buddies in the evening and have a pint of root beer, I'm sure, and make fun of people's arguments in science and, just having a good old time poking fun at people. And he read this from Planck and he said, no, Planck is wrong. It really is occurring that the energy that's being produced by these, whatever is giving off energy in a black body, is coming in quantized units. He said that it had probably quantized oscillators. So things that, can have one frequency or a harmonic of that, just like if you have a wave on a string, you can have one frequency, you can have a harmonic above it. And so he said that would make perfect sense. And so he wrote one of his 3 papers. In 1905, he wrote 3 papers that were each, I think, worthy of a Nobel Prize. One was on Brownian motion, the little vibrations that were seen in pollen as it floated in water, looking through a microscope. Young had looked at it and attributed it to, quote, cavorting beasties. At least that's what I learned in high school biology. If you've had more than that, then you're above me. And by cavorting beasties, what he meant was some submicroscopic type of living thing that was making them oscillate. And Einstein said, no, it's just the actual motion of the water molecules. We have the kinetic theory saying that temperature is related to the motion. Those water molecules are themselves moving. Still water's not still molecules, and the pollen's so light that you can see it vibrate. So that's one of his papers. Then he wrote the paper on special relativity, on theory of special relativity, which most people think that's what he got the Nobel Prize for. And then he wrote the paper on the photoelectric effect, the quantization of light, and that's what he actually got the Nobel Prize for. So 1905 was a really important year. Modern physics is the physics that has developed since Einstein came through with these new ideas. So now a history of the photoelectric effect. Probably revisionist history, but the history I've read says that Heinrich Hertz first observed the photoelectric effect. From what I have read, by observing it, what he observed was he was testing to see if James Clerk Maxwell, you do know his last name was Clerk Maxwell, family name was Clerk, and his father adopted Maxwell as an additional name. So Heinrich Hertz was testing Clerk Maxwell's theory that light and electromagnetic radiation were the same thing. Basically, Clerk Maxwell said, well, electromagnetic radiation, I can calculate its speed. It turns out to be the same speed as the speed of light, hence they're the same. Kind of like saying I walk the same speed as that car is driving, so we're the same thing. It doesn't logically hold forth. And so Heinrich Hertz was actually studying to see if light and electromagnetic waves had the same behavior, that is, the same refraction, bending when it goes through change in speed medium, or medium with different speed, and diffraction, bending around objects, and reflection, testing these things. And in the process, he was using a spark gap generator. So he had two globes, and he would put an alternating current so that you'd have one globe is large positive, one is large negative, and an arc goes across, and then the other way, and the arcs just go back and forth. That's how he was creating his electromagnetic waves, was through the spark gap. And he knows that when he polished those little globes, that it would arc easier. And based on that work, I am pretty sure the rest of this came from other researchers. It's determined that the magnitude of the current depends on how bright. If you shine ultraviolet light on it, you get current. The higher the intensity of the light, the more current you get. And if you change the frequency, so if you go from ultraviolet to violet to red, the energy of the electrons coming off goes down. And so in 1905, Einstein's paper said that what you have is light has packets of energy, which he eventually called photons. And if that packet of energy is absorbed, then it can transfer all or some of that energy to an electron. If it transfers all, the electron would come out with, at most, an energy equal to the energy of the photon that came in. And so it gave a good working experiment that could be done to test if light behaved as a wave or a particle. And of course, in this test, light behaves as a particle. Now, before Einstein, you can go way back, you had Isaac Newton believed that light was particles, his corpuscular theory. And so he said light's a particle, and he explained everything. He explained refraction incorrectly, but as a particle behavior. And then Thomas Young did his experiments with slits. And with the double slit, he saw that light would interfere with itself. Particles can't interfere with themselves. They go through one slit or the other slit. They can't interfere with themselves. And so Thomas Young determined, no, light has to be a wave. And so we went from Newton saying light's a particle to Young saying light's a wave, and now we get to Einstein saying light's a particle again. The result is now we say, well, Thomas Young's experiment it's not refutable. It's definitely got to be a wave. Photoelectric effect, it's definitely got to be a particle, and so we say light has both wave and particle behaviors. And you see in 1915, Robert Millikan confirmed it. Now, some other steps along the way, you see in 1916, Einstein revalues theory, and that's when he determined that all light, regardless of its source. Remember I said when he first adopted the whole Planck's idea, he said it's oscillators producing the light, so it makes sense that they have, the fundamental frequency or resonant frequency and overtone, if you will. Well, he said, no, all light actually comes in packets. It doesn't matter what the source is. So when he revisited it, he came up with that idea, and that the light actually carries momentum. So basically, you think of light like a massless BB. And Compton, you know of Compton scattering, I assume? So Compton was looking at scattering by metallic foil, and he saw that he got, you put in one frequency distribution. So here's frequency on this axis, and you have the intensity on this axis. So you put in something like that, and after scattering, he got something that was like that. So that he had two frequency peaks instead of one. Now, by wave theory, if you stay in the same medium, you cannot change frequency. Actually, even if you don't, you can't change the wavelength unless you change medium. The frequency just can't change. And so that did not agree with the wave theory of light. And so using relativity along with this idea that light comes in packets, Compton was able to show that the second peak was due to a change in momentum of the photons. So an experiment confirming that photons have momentum. And in theory, the momentum of photon is, here I remember to change the font, h times the frequency over the speed of light. And this is just going through the equations so that you get to the Compton scattering equation. And so Compton's results can be explained by, you have the scattering from an electron causing the shift we see here. The scattering from the entire atom also occurs, but since the mass of the atom is really large, and that's in the denominator here, the scattering from the atom results in a non-observable change in the wavelength. So Compton's scattering can be explained with relativity along with a particle theory of light. I don't know if you've looked at any of the resources. I have what I consider a truly interesting article, probably because I've been in physics far too long, because when I was in college, I would have thought this was just boring stuff. This is an article by Felix Bloch about the early days of quantum mechanics. He worked, he first was acquainted with Schrodinger, and then he actually was the first graduate student under Heisenberg. He's famous in his own right, but it's pretty amazing that he was just living there when this stuff was being developed. I find it interesting that he says Maurice, and how do you guys say that guy's last name?
Roy.
Dude, that's like right. I've always said de Broglie, but
Yeah, Lang kind of banged it into our head.
okay, good. But have you ever seen his first name is Maurice? No. I mean, his first name is Luis. It's like Luis, Patrick, blah, blah, blah. It's like 5 names all chained together. So this article, I mean, I really encourage you to read it. It's just, nothing in here is going to be tested. It's not something that you need to know. But it's really interesting just to see what it was like in those days. And you just keep seeing names that are so famous in physics, and they're like all there together. And so, yeah, I linked the article there so you can read it. Anyway, so Louis de Broglie, he said, well, wait, look, light can be either a wave or a particle. What's so special about light? What about me, little old me? Shouldn't I be able to be a wave or a particle too? And he determined that we should be able to take any particle and say that it has a wavelength that's Planck's constant divided by its momentum. It's really only useful for electrons. I have a slide coming up that shows all the things that we've actually been able to observe the wavelength for a particle. But Louis de Broglie said, we should be able to treat something like an electron or even a proton as a wave, that it has a wave nature as well as a particle nature, just like light has a wave nature and a particle nature. And so this is where that article that I pointed to really leads you to. I have a few more things here, X-ray scattering. I'm not exactly sure why I have the X-ray scattering now that I think about it. The Davison-Germer experiment that shows that electrons will scatter the same way that light did, as Bragg showed. So that was showing that electrons have a wave nature, since scattering is a wave process. It's not a particle process. So we have seen diffraction from electrons, protons, neutrons, hydrogen, helium, and Buckminster fullerenes. Those are the entire list of things that have been observed to have a diffraction or a wave nature that are typically thought of as particles. And, electrons, is an electron a particle? What do you know about electrons in their physical properties, like size, for instance?
They're really small.
Yeah, they're really small. That's really all physicists do know about the electron size. Some believe that it's just a point that has no volume whatsoever. Others believe that it has a finite volume, and you can calculate it's got to be smaller than this tiny amount. So it's still an area that's not fully understood, but it's really tiny. Protons, we can recognize those are bigger. And neutrons, roughly the same as a proton, right? Hydrogen atom, you've got the nucleus and you've got the electron cloud. Now it's getting more fuzzy because that cloud is, as we understand from quantum theory, fuzzy. And helium bigger. Buckminster fullerenes, now you have a whole bunch, 60 atoms or so? That's a reasonable size physical object there. And even those Buckminster fullerenes with a reasonable size physical object, they've still been observed to show scattering, that is, to have a wave behavior. Now, finally, what time is it? We got 17 minutes. We're good. I just wanted to make sure I don't keep you here for half of the next class period. Final thing, I think, for today, talking about the development of quantum theory. We've talked about how black body radiation led to it. And if you go to that article that I showed you, it talks further about how Schrodinger was really excited about reading about de Broglie's idea of things like electrons having waves, and Debye was all like, "You're teaching it like a kid, man. It's got to have a wave equation if it's a wave." And so then Erwin Schrodinger said, "Yeah." And so we went and spent some time, and he actually developed a wave equation, which has become super, super important in quantum physics. It's like the subject of chapter 1 of our textbook, the Schrodinger equation. And if you read that article, you'll see, Bloch is talking about, nobody knew what the wave function really meant. We had a wave equation, we could find a wave function, we could find cool things from it, but what did it really mean? And even some of these great minds were like, you're trying to put too much meaning into something that has no meaning. So that is a big development. That's how we got to our quantum mechanics. Werner Heisenberg, who of course Bloch was the first student under him, he came up with a completely different approach for the same quantized ideas because of looking at atoms. So that's why we have to look at the atom here. We had Schrodinger use the wave ideas from, let's say from Louis de Broglie, and Heisenberg was simply trying to look at properties of atoms and the electrons specifically in the atoms, kind of threw up his hands and said, what else can I do? Because we don't know things. So Geiger and Marsden did the famous gold foil experiment, which everybody knows is the Rutherford experiment. Rutherford was the head of the lab. And if you've known anything in physics, you know the person that's the head of the lab is the one that gets all the credit. And then under him, his primary researcher was Geiger, famous for the Geiger-Muller counter, or people have to call it the Geiger counter. And then they had the newbie in the lab, the person who is, the new grad student or postdoc that was Marsden. And so from the history, that's not how you spell Marsden. From the history I've read, Geiger went to Rutherford and said, young Marsden here has developed enough. He's ready to take an experiment on his own. And so Rutherford said, okay, Marsden, here's something you can do. We know that gold is malleable. So if we smash it down to a really thin sheet, we should have basically a whole bunch of really thin positive charge. Because at that point, they thought that, well, the plum pudding model, they thought that you just had positive charge spread evenly everywhere in matter. But Thomson had already determined that there were electrons in matter. So they had like little raisins, the electrons periodically spaced in that. So if you smash it all down, you'll mostly have particles just going through the nebulous positive charge. If you're lucky, you might have the particle hit an electron. So they used alpha particles, which they knew to be much heavier than electrons. And they figure if the alpha particle hits an electron, it'll just slow down a small amount. We'll see a slight change in speed. And if it misses, it'll just go through. Well, Marsden does the experiment, and he finds that some of these alpha particles bounce straight back at them. And you don't have a big heavy particle ever bounce straight back off of a small particle. It's like you throw a bowling ball at a fly, and the bowling ball bounces back at you off of the fly. In fact, the actual description that Rutherford used when he goes on the circuit to become famous, or famous speaker talking about what he discovered, was imagine if you take a piece of tissue paper and you shoot a cannonball at it, and instead of going through the tissue paper, the cannonball bounces off the tissue paper. That's how they felt about it. And so they quickly said, it can't be just nebulous positive charge. There must be something really massive in there. And so he said that charge must be all at one lump that we'll call the nucleus. And he was able to determine, because he's shooting these alpha particles with a +2 charge, he's able to determine by the change in scatter, the change in how it bounced off, with energy, what the actual size of the nucleus was. And so he was able to get some real specifics about the nucleus. And so he came up with a planetary model. That planetary model said that, I have it right there. That planetary model says that you have, I swear I have pictures here. That's going to the Bohr. Okay, forget it. I have pictures of the Bohr model. That planetary model says that atoms are probably like a planetary system, where you have the massive object at the center, the nucleus, and then you have the less massive objects that are like planets orbiting. Now, we know, of course, that our planets don't do circular orbits, but he constrained them to circular orbits. And it seemed like a good theory, except for some real significant problems. If I have a charged particle and it accelerates, speeds up, slows down, or changes direction, electromagnetism requires that it must radiate. So energy has to be lost if it's changing direction. Well, if the electrons are orbiting the nucleus like a planet, electrons clearly have charge, they're accelerating, they're going to give off a lot of radiation. So in less than a nanosecond, electrons should always collapse into the nucleus. That's kind of a flaw. And the hydrogen emission spectrum shows clear, distinct energy levels. That is, there's only certain energies you can get from light coming from hydrogen. And, the planets, we have nothing that says planet can only be, 1 astronomical unit away from the Earth or 2 astronomical units. It can be any distance away. So those were some significant flaws. So Niels Bohr came over and worked with Rutherford, and in just a matter of years came up with a new model that was a quantum model. His model said that electrons have a stationary energy. So they have certain energies they can have, and they can't just have any continuous energy. And because they can only have certain energies, that whole law of electromagnetism that says if you have an accelerating charged particle, it gives off radiation, can't be obeyed. Can't be obeyed because that would require changing continuously in energy instead of having a quantum jump in energy. So it's kind of like saying, I'm going to impose a new rule that supersedes what we understand from electricity and magnetism. And furthermore, he said that angular momentum is quantized. It comes in only specific units of energy. You can see why we're using F for frequency, because if I had V for speed and F for frequency, or no, I said it the wrong way. F is what we use in general physics because you use V for speed and nu for frequency, and it looks wrong. Anyway, the angular momentum is quantized. If you're going in circular orbit, you have, MVR is your angular momentum, and that's equal to an integer number. So that n is a quantum number. It's just an integer multiplied by h over 2 pi. This h over 2 pi appears everywhere in quantum mechanics. So I'm going to introduce right here an abbreviation for it that you guys probably know everything I'm talking about today for the most part, right? It's just the random stories you don't know all the physics you do. So we have this here. Some people call it h slant. Some call it h bar. Some call it Planck's constant, which is really confusing because then you have two different Planck's constants. Some call it Planck's reduced constant. And so that Planck's reduced constant was just a unit of angular momentum, and it can have 1 times it or 2 times it or 3 times it, is what Bohr used as one of his quantum condition hypothesis. And so here we had quantization. Now, this has some great successes. It predicts perfectly well what the energy is for the spectrum of lines you see in the hydrogen atom, the Balmer series, the go down one, the Lyman series, go up one, you have the, Balmer, Lyman, Ballman, somebody, I don't know. I can't remember all of them now, which is bad. But those spectra are perfectly explained by the Bohr model. And it gives you a radius for electrons orbiting the nucleus. And it gives you a speed for electrons orbiting the nucleus. All of these come from one quantum number. Only problem is there's plenty of flaws in that as well. So here, let's focus on a success. The Stern-Gerlach experiment was looking at the angular momentum of silver atoms, neutral silver atoms. When I say angular momentum, this gets to a first area where people usually are a little fuzzy. He had a magnetic field gradient. What does magnetism have to do with angular momentum? It seems like they don't. But if you have a charged particle with angular momentum, that creates a magnetic moment. Just think about if I have a charged particle that's going in a circle, like in a solenoid, that creates a magnetic field, right? Current in a solenoid creates a magnetic field. And so when we talk about the angular momentum, the observable, the thing that we can actually measure is its behavior when it's put in a magnetic field. And so anything that has to do with angular momentum is measured with magnetism. So an electron, we're getting into the period where people notice that electrons have a behavior when they're in a magnetic field. They have a magnetic moment. And so they said, well, obviously, then the electrons must be spinning. They're going like this. And so they called that, the thing they used to describe the magnetic moment of the electron, they called the spin. But with our current understanding of electrons, remember I talked about its size, and some people say it's just a point, and we can calculate it's definitely smaller than this. There's no way to get the magnetic moment of an electron with its charge and its maximum possible size. So the spin of an electron cannot be the result of an electron spinning. So it's an inappropriate term, but it's one that was given. It was believed to be true at the time, and we still call it the spin. So when you talk about the spin of an electron, you're talking actually about its magnetic moment, about its magnetic moment that apparently is intrinsic. It just behaves like a bar magnet for no good reason. So the Stern-Gerlach experiment is looking at the magnetic moments of the silver atoms. And under normal physics, you'd say, well, the magnetic moment could be anywhere between here and, just going around a circle. And so when you have the particles go through this, this changing magnetic field, you should have the particles spread out based on the orientation of that magnetic moment compared to the orientation of the magnetic field. And so the classical problem would have seen a continuous distribution of magnetic moments between the maximum one direction, the maximum the other. But the actual experiment only showed two orientations, what we would call up and down if we were talking about an electron. And so it showed that these silver atoms had discrete angular momentum. Well, a very important theory just for all of physics, Bohr's correspondence principle. If you get to the situation where the separation between quantum states is so small as to be indistinguishable from continuous, your results would better match with conventional physics. That's what the correspondence principle says. So you can't come up with a new physics that contradicts an old physics and have them both be correct in the area of overlap. In the regions where they don't overlap, that's fine. But in the areas of overlap where they're both supposed to be valid, they better agree. Okay, so Heisenberg, he noted from the work here that it's not possible to determine the path an electron is going to take as it orbits the nucleus. And basically he's pulling his hair out. What do? I can't track the path. And, we live in deterministic physics here. And finally he said, forget it. I'm just not going to worry about that. I'm going to start saying, what can I measure for the electron? Well, I can measure how it behaves in a magnetic field. So I can measure its magnetic moment. And I can measure, and he starts identifying the things he can measure. And he just starts making tables of the values and how the values can change. And then Heisenberg takes his tables to somebody else and says, I don't have the math skills for this. I don't know what to do with this. I can't remember the names of anyone in this story, which I know takes away some of the strength of the story. That guy sends it off to somebody who's studying matrices, and he says, well, yeah, this is just matrix math. And sends it back, look, you just do this, this, and this, and boom, we had a matrix method to deal with the observables, the things we can actually measure for the electrons in an atom. And so that's what Heisenberg's approach was. It's a matrix method of tracking the observable things, the energy, the magnetic moment, and a few other things. So that's one method for doing quantum physics. The other method is using Schrodinger's wave equation that he came up with. Now, this wave equation is basically using Hamiltonian mechanics. Have you guys taken dynamics class yet? No? Okay. In dynamics class, you learn things like the Hamiltonian method or the Lagrangian method. And this is basically, if I understand it right, the Hamiltonian method. You have operators. Operators are mathematical functions that operate on another mathematical function. One of you is a math major, probably is like way up on this. Okay. So we have an operator here, and let's start with the momentum operator. And we use different symbols to indicate operator, like that to indicate operator. The momentum operator is something like h bar over I del. Okay, I think that's it. I didn't look it up, so I see you got a teacher behind you or somebody behind you. I'm like, what if I didn't remember it right? Is that Greg? So you have momentum, and of course we know that kinetic energy, or T is the symbol is used in your high level classes, is 1/2 mv squared, or in terms of momentum, that's momentum squared over 2m. And so the kinetic energy operator, the T operator, so I'm doing both things here, is going to be the momentum operator squared over 2m. So that's just going to be h bar over I got to dot them because they're vectors. And so that's, and then all divided by 2m. So that's minus h bar squared del squared. And so our kinetic energy operator is that right there. And I just have this picture for the Schrodinger equation because everybody knows it's cool to have the Schrodinger equation tattooed on your back. Although we do know also that the Bible says it's a sin to tattoo. So we have the kinetic energy operator, and then we have our potential energy operator here is equal to, and notice those are both acting on psi. That thing that back when Schrodinger came up with this, he had no idea what it meant. And then we have this here. We have our final operators, the energy operator, where the energy operator is equal to IH bar partial derivative with respect to time. Okay, we're out of time. We'll start in with actual quantum physics Wednesday. Remember, you do have a homework assignment. You have the homework assignment. You have the answer. You have to render your own answer in your own form so it follows my format. Okay, any questions before we go?
When it comes to reading,
yes.
Like, how do you want us to do it? You want us to like read a section before we go over in class or after?
Okay, so here's the schedule of everything in the class. And so for next class period, I will be covering chapter 1, section 1. And so it is going to be most efficient if you've read it beforehand. I was actually going to try to use that perusal, but they said that they can't get our textbook. So no. So yeah, it would be most efficient if you've read through it and you've thought like, I understand this and I don't understand that. So you can totally ask me questions. And I actually was going to, I may actually have it in syllabus because I had it at one point. You need to ask me questions before like 10:30 your time, because I have class from 11 o'clock your time until the end of this class. So I can use those in class. Because if you have questions beforehand, you let me know beforehand, I can be more prepared to go to what you have questions on. And so, yeah, you can see what days the homeworks are due.